Swayam Prabha. Digital India. Educated India.
Okay, so far we have been talking about metals, the structure of metals and alloys, how the metals derive their strength. Now we will change gears a little bit to the strength of polymeric materials. Now polymers are essentially chemicals. Basically these are chain type of compounds where the chains are made of carbon and hydrogen primarily, but then you can also have many other constituents like chlorine, fluorine and so basically halides. So essentially the polymeric materials similar to ceramics are compounds. So we have three types of materials, metals, ceramics and polymers. Now metals are the ones which are naturally occurring and they are extracted from natural ores. However, polymers are artificial materials. These don't occur in nature, but these are made by human beings. They are man-made materials. So this polymerization which takes place is entirely a man-made process. Similarly, ceramics are the ones which are naturally occurring as well as man-made. For example, glass is something that can happen in nature, but in case of most of the engineering ceramics, we deal with man-made ceramics where artificial processing is used for making the ceramics. So now we will look at where the polymers derive their strength from. So very clearly it is the interatomic bonds between carbon and hydrogen, and so the structural characteristics affect the properties of polymers. So what are the structural characteristics? Well, you have a polymeric chain. Larger is the length of the chain, more is the molecular weight. So each chain forms one molecule, and the size of the molecule determines at what point that polymer is going to melt. So basically the properties of a polymer, unlike metals, depend significantly on the length of the chain and the extent of polymerization, meaning the molecular weight of the polymer. So the degree of crystallinity, density, strength, stiffness, ductility, these are the parameters which we would like to investigate when it comes to polymeric structures. Now polymeric structures can be crystalline, can be amorphous. Now if you take a crystalline polymer, unlike metals, it is not 100% crystalline. So a polymeric structure may not be fully crystalline, it is usually partly crystalline. Now in metals, it is very difficult to have amorphous structures because the most stable location of the atom is reached by each of these individual atoms. So we form crystal structures at different temperatures. So different crystal structures in metals are found at different temperatures. But in case of polymers, what happens is the polymeric chains they get laid out in such a way that they can form regular pattern of carbon and hydrogen atoms. So for example, chains folding over each other can form a regular pattern of carbon and hydrogen atoms, due to which it can give an impression of an ordered arrangement of atoms. So what is crystallinity after all? In case of metals, we have seen that it's an ordered arrangement of atoms, and in metals we have face-centered cubic, body-centered cubic, 14 Bravais lattice structures are available in metals. But in case of polymers, what crystallinity means is ordered arrangement of atoms. Okay, ordered arrangement of atoms is the one that gives polymer the crystallinity, and therefore more is the ordered arrangement, naturally more is the strength of the polymer. Amorphous polymer will have relatively lesser strength and therefore a low melting point, whereas a polymer structure with higher value of crystallinity, meaning larger range of order, will mean that it will have a greater strength and greater melting point as well. Degree of cross linking is very important because these are chemicals formed by covalent bonds. So, carbon hydrogen bond and most of these bonds in polymers are covalent bonds. Now, these covalent bonds can be double bond, triple bond and so on, and then the degree of cross linking results in a polymer having very high strength and a larger melting point. So, for example, if you take bakelite, polymers which are thermosetting polymers as we call them, they have great deal of cross linking. Cross linking polymers include let us say polyurethane for example, or bakelite. So, these polymers will have a lot of cross linking taking place, and this cross linking gives them the strength. The strength is very high, but then we cannot expect ductility from these, because now the mechanism of ductility is completely different in case of polymers. Now, unlike metals where we had dislocations and dislocation movements taking place, so that the material can deform, right. When a dislocation in metal moves from one location to another, you see that in the form of permanent deformation. Now, if you want to permanently deform a polymer, you are effectively deforming a bunch of polymeric chains. Okay. You are not deforming a metal like structure, but it is a polymer structure which is a chain of covalent bonds. So, these chains of covalent bonds are being deformed, and therefore, this deformation mechanism is going to be completely different as compared to a metal. Now, for example, you extrude metal, right? You extrude metal and you find that ductile metals are very amenable to extrusion, and they get extruded very easily without much of a force, and the extrude diameter and the diameter of the die are practically the same. Now, when you extrude a polymer, let us say you extrude a polymeric billet through a die, then what happens is at the end when the material comes out, then it swells. So, the swelling of the polymer is much larger than the elastic strains which are released in case of metals. So, basically polymeric chains therefore have a completely different mechanism of deformation. Deformation occurs by sliding of polymer chains relative to each other. So, if the polymer chains can slide very easily with respect to each other, then they are able to deform very easily. If they are cross linked, then there is no sliding that is easy, and therefore the chains refuse to move with respect to each other, and therefore these cross linked polymers are like rigid structures. Similar to ceramics, they do not have any kind of ductility. So, they have high strength and they break without any deformation. So, polymer structures of what is called what we call as thermosetting plastics, for example, these structures are very strong but have poor ductility. Thermoplastics are like metals, similar to metals, like they have a specific structure, and of course, the melting point again depends on the molecular size, but then they are amenable to deformation and so on. We will see the differences between thermoplastic and thermosetting materials as we go along. So, the polymer chemistry determines the melting point and glass transition temperature. This is another temperature which is typical to polymer chemistry. So, we see that there are different kinds of organic molecules. Methane, for example, is CH4, where this is the structural arrangement, and the boiling point is minus 164 degrees centigrade. Okay. Ethane has got C2H6. So, basically if you take away one atom of hydrogen and add one more CH3 group over here, then you have C2H6, which is ethane, and it has got a higher melting point of minus 88.6 degrees centigrade. You increase the number of carbon atoms, you make it C3H8, the boiling point increases further. So the same thing will apply to melting point also. So now melting point is something which is in some of the polymers is after the glass, so-called glass transition temperature. So we will discuss these two properties a little later. But then the boiling point as well as the melting points both would vary in a similar manner as the length of the chain continues to increase. So you have butane which is C4H10 minus 0.5, and then hexane has got 69. So plus 69 degrees centigrade is the boiling point of hexane. So at room temperature, therefore, hexane would be a liquid, pentane would be a liquid, whereas butane will be gas. And so all these will be methane, ethane, propane, butane will all be gases at room temperature condition. Here what has been shown is chains, polymeric chains with carbon and hydrogen atoms, and these chains wind over each other. So these polymer chains can wind over each other, and then you see that you have a regular array of these polymeric chains, as a result of which you can get an impression of crystallinity, meaning a regular arrangement of atoms in this particular area. So the properties of the material will be similar to a crystalline material, meaning the property will get enhanced because of the fact that in all three dimensions the material is bonded, and therefore there are forces of attraction which keep the atom in place more firmly than what it would have been if it were just a straight chain compound. So for example, if this is just a straight chain, then you will have certain boiling point, but now if it gets folded over something like this, then you will have when boiling point may remain the same, but then the melting point will tend to increase. So if you look at the straight chain versus branch chain compound, so this is a straight chain. So as the chain length increases, your boiling point also increases. So you have a relatively shorter chain of 3 carbon atoms, and the boiling point is lower than the boiling point over here. So the properties of the polymer depend entirely upon the size of the chain and the entire structure. You take macromolecules. So macromolecules are the ones which we normally use for our engineering practice, and these are macroscopic molecules. So unlike chemical molecules, like one atom of methane or one molecule of methane is not visible, it is a micromolecule. But then you take a macromolecule which has got a large number of carbon atoms, so there you will find that the size of the molecule itself is capable of being detected by the naked eyes, and therefore the molecular weight is quite significant. So as opposed to methyl group or to methane, the molecular weight of a macromolecule is extremely large as compared to that of methane or ethane or basically single molecule. So here you see that this is a characteristic unit. R is a group like methyl group, ethyl group or phenyl group. So ROH is basically characterizes alcohols, and since if R is CH3, then it is called as methyl alcohol. Similarly, ethers have RO R dash. So CH3O CH3. So these are the ethers like dimethyl ether, and so all these bonds are single bonds. There is no double bond which is present over here. So alcohols and ethers, you don't have any double bond being present, all bonds are saturated. Now, if you take acids, then the COOH group is designates an acid. So, you have R signifying either CH3 methyl, so methyl group. So, it is acetic acid. So, I mean this is the very commonly known acid which has got a double bond over here with oxygen. Then you have an aldehyde group CHO. CHO is the aldehyde group. So, formaldehyde is HCHO, and there are, so instead of H you have CH3, then you will have CH3CHO, another aldehyde. So, there are a number of aldehydes which are possible, where you have C2H5CHO as another aldehyde, but each one of them will have their own behavior, own molecular weight. Now, here this is a single molecule of an aldehyde. Now, if you want to make a macromolecule, you will need to polymerize it. Means that you will need to put it into put multiple units of this in a single chain. So, instead of having say this carbon atom R and R dash there, you could have this polymerized. So, for example, if you were to polymerize this, then this double bond might go, and then it will be available for polymerization with the neighboring atom. So, basically polymerization takes place very easily, particularly where you have more of double bonds. The double bonds are significantly present. You have aromatic hydrocarbons because you have benzene ring over here. So, you have a benzene ring with carbon atoms joined with each other with alternating single and double bonds. And this benzene ring is for example has phenol. So, there are different positions, alpha, beta, meta, tera and all that. So, you have phenol with OH group being attached to at this position. Depending on the position to which OH group is attached, the properties often change. So, basically in organic molecules, in organic molecular structures, the position in which each of these groups, CH3 groups for example, get attached, or OH groups get attached, changes the properties of the resulting compound. And then if you were to polymerize it into macromolecules, then you can get different polymers from the same, not from the same material, but from the you can get different polymers from different arrangements or from different locations of these. So, this will be called as monomer, and then you polymerize this, you will get a polymer, and therefore you have you will get a structure of due to repeating units of this type. So, if you take polyethylene, you have an ethylene here. Okay, so you have all hydrogen atoms will mean ethylene, but and then you polymerize it, it becomes polyethylene. Now, if you put R as CH3 here, instead of normally it would be H if it is polyethylene, but then if you put CH3 over here, then this R stands for CH3, then and you polymerize it, it will become polypropylene. Similarly, if you substitute these hydrogen atoms all four with fluorine, then you will have tetrafluoroethylene. So, there are a variety of compounds which are possible by either substitution or by attaching a different functional groups over here, CH3 and so on. So, these are molecules, these are monomers which are which when repeated several times will result in a big macromolecule. So, you have tetrafluoroethylene, which is when polymerized becomes polytetrafluoroethylene, which we call as PTFE, and PTFE is used for coatings, a number of coatings on these are lubricating type of lubricating tapes are made out of it, lubricating coatings are made out of it. In our household utensils also we have PTFE coated pans and so on. So, it's a very commonly used polymer, but the monomer, the secret of that polymer lies in this particular structure, where you have a double bond here which gets converted to a single bond at the time of polymerization. So, wherever you have double bonds, they help in generating the polymer. Similarly, polyvinyl chloride. So, you have so this is vinyl chloride where you have this R being replaced by chlorine, right. So, this is vinyl chloride, and you polymerize this, it becomes polyvinyl chloride. Now, the melting point of polyethylene. So, you have the basic structure of ethylene, you have you can transform it by substituting hydrogen by fluorine, or one of the hydrogens here by chlorine, and you can get three very different polymers: polyethylene, polyvinyl chloride, PTFE, and polypropylene. So, you can get polymers having very different properties, meaning their melting points are different, their there's rates of softening are different. So, all the mechanical behavior of all these polymers changes significantly by the presence or absence of a particular group. So, for instance, if CH3 is present instead of R, then you get a very different property. In fact, in most of the batteries in electric vehicles, you have the polypropylene being used as a material for the separator, and that is because it has got a metastable phase which changes during deformation and generates the kind of porous membrane which is needed for a separator in the batteries. So, I mean, you can just remember this that a simple material like polypropylene, by virtue of its its chemical nature, influences the mechanical nature, and therefore it has got certain applications which are characteristic of that particular material. There are a few other polymer structures like polymethyl methacrylate, PMMA, which is also called as perspex. So, you see that you have methyl methacrylate. So, now you have chain double bonded chains over here, and so again you will have a repeat unit which is quite heavy in terms of molecular weight. So, the single molecular weight itself is very high, and therefore, the mechanical properties of PMMA would be drastically different from the mechanical properties of the polyethylene or polyvinyl chloride, where the repeat groups themselves are relatively small and much lighter. We have phenol formaldehyde, which is called as bakelite. Now, this particular structure is a repeat structure involving a benzene ring, and bakelite can form cross-linked polymer. So, this can form cross-linked polymer on being converted to a thermosetting plastic. So, initially you may have granules of this structure, and then when you actually do the manufacturing, there is cross-linking taking place with water getting eliminated, and then you get the cross-linked polymer of very high strength. So, phenol formaldehyde, which is called as bakelite, gives you a thermosetting polymer of very high strength, and it has got this kind of structure. Polyhexamethylene adipamide is nylon 6.6 or 6,6. So, this is so this nylon is again an engineering material. In fact, many of the hammers use, instead of steel, the hammering element is made of nylon, because if you do not want to cause severe dents in the item to be hammered, then because steel is too hard a material for, I mean, it can be too hard a material for a substrate, and therefore it may be required to use a relatively softer material for hammering. So, you can use nylon 6 hammer element to do the hammering, so that no dents are left behind, and I mean, no unintentional features are left behind. So, many tools are made with nylon 6, and this is a very strong material. So, as you see here, the length of the molecule, the size of the molecule, the molecular weight itself being this large, the overall strength also increases accordingly. Similarly, polyethylene terephthalate, PET. So these are PET bottles. We use PET bottles, right? So polyethylene terephthalate is a material from which some food grade plastic or something is or such articles are made. So you have drinking water bottles or lunch boxes, etc., made from this PET material, and again this has got good amount of strength. So again this has got a good amount of strength. So compare these molecules. These are monomers here, but then if you look at these polyethylene and PTFE and all that, these monomers are much smaller in size as compared to this one. The single monomers are. Now polycarbonate is another material where you have in fact these are usually many times transparent in nature. These polycarbonate sheets which we use are transparent in nature, so one can make transparent articles from this particular material. And again the properties depend significantly on the nature of bonding that you see over here, and when it becomes polymerized. So this is a monomer which is a repeat unit, and when this gets polymerized, depending on how often this has been repeated, the weight of the molecule will therefore be determined by that. So if you look at the molecule of I think this HDP or something. So here you have the nucleation site, and then you have the direction of spherulite growth. So the chains grow in different directions from here, and you get a macromolecule which is a combination of several chains here. So basically when we talk about a macromolecule, the way we see it with our eyes, because the micromolecule is not visible, but a macromolecule is something that is visible, it is tangible. So you have several chains, long chains which are present, arranged in a specific order, and that is what is shown over here. So here you have the polymer chains being arranged in a spherulite manner. So if you look at the a polymer, let's say you want to manufacture something out of polymer, then you have material available in polymer granules. Remember that these are artificial materials. So these are materials made by mankind, and therefore every granule might not be the same or will not be identical as the other, and so it may have distribution of different sizes of molecules. So it may have so one particular granule could have a different distribution. So if you look at this, molecular weight is distributed. Okay, so you have weight fraction versus molecular weight gram per mole, and you see that for between 5 to 10 the weight fraction is very small, and most of the weight fraction, molecular weight fraction, is between 20 to 25 into 10 to the power 3 gram per mole. So now compare this with metals. If you take metallic materials, you have atomic weight. So many grams per mole, 55 grams per mole, 63 grams per mole. Now here you are talking in terms of thousands of grams per mole. So you have 20 to 25 into 1000 grams per mole. So that is the difference between the kind of weights we talk about in case of metals as opposed to polymers, because polymers you cannot consider atomic weight, you have to consider the molecular weight, because molecule of polymer is the one that governs the strength of the material, the structure of that particular molecule. So the structure at the molecular level governs the mechanical properties, the structural behavior of the material. So there is a significant difference between how metal properties are derived and how polymer properties are derived. Metallic properties are derived based on interatomic attraction, interatomic forces, whereas the polymer strength or polymer properties are derived from molecular level attraction or molecular level phenomena to a large extent. So, if you look at the melting point, for example, again with a different molecular size distribution, you will have a different melting point. So, unlike metals where you have fixed melting point, of course, when you add some alloying elements, you can change the melting point, but then that also is fixed. So, for a given alloying condition, the way the material will behave from solid to liquid or from while solidification is all fixed. There is no significant variation in that. But in case of polymers, the melting point itself varies very significantly depending on the molecular weight. So, it is possible that in a same quantity of polymer, let us say you have a number of polymer granules, it is possible that at a given temperature some polymer granules have molten, some have not. Whereas in case of metals, if you take if you say that I have an alloy of particular composition, the alloy will melt at a particular temperature. So, at a liquidus temperature it is going to melt, and anything higher than that it is always going to remain molten. But in case of polymers, that does not happen, because you have different molecular weights, or you have molecules of different weights present in the polymeric granules, due to which some melt, some do not melt at a given temperature. So, you have to make sure that the highest I mean the molecule with the highest molecular weight, or basically the granule which has got highest melting point, has also molten. So, the melting point is really not very fixed in case of polymeric materials. Now, if you look at the ways to represent the molecular size distribution, you have either number fraction in terms of molecular weight. So, you have let us say 10% of or maybe 5% of molecular weight up to 10 into 1000. So, 10,000 gram per mole. Similarly, you would have let us say 15% that is number fraction of molecular weight involving 10 to 15,000 gram per mole, and this way here you will have the maximum, namely very close to 30, maybe 27 or so, between 20 to 25,000 gram per mole. So, this is one way of representation. The other representation is weight fraction. So, you have weight fraction of different molecular weight molecules. So, what it means is, if the molecular weight is low, of course, it is a small molecule having a relatively lower melting point. So, if you take a molecular weight of 5 to 10 into 1000 gram per mole, it is a relatively smaller molecule as compared to 30 to 35,000 gram per mole, right. So, this will have a relatively lower melting point, lower strength and a lower chain length. Similarly, you have molecular weight of slightly higher magnitude. Naturally, this will have a greater melting point. This will have much greater melting point. This will have greater melting point, much greater compared to this one. So, now you have a range of melting point, the range of strengths which are available for in each of these different molecular weights. And so, it is for one to decide what is the strength you want for in the final component you are trying to make, and what is the strength. So, what is the mixture of strength that you would like to use in the raw material, so that you can have an appropriate mixture of molecular weights being used for making that particular product, and you repeatably get the final properties. So, in typical polymer, you have molecular weights being distributed, and they are not distributed according to a Gaussian distribution. So, you have amount of polymer versus so this is number average and the weight average. These are not two different these are not the same things. So, these are two different things. So, number average is something here with the same molecular weight, and the weight average is relatively higher at the higher molecular weight. Now, dP represents the degree of polymerization. So, we have seen that a repeating unit when repeated n number of times, several number of times, gives rise to a macromolecule and a molecule of a large so it's a macromolecule having greater molecular weight as compared to the monomer. So, degree of polymerization would mean m bar n upon m, where we are talking about number average molecular weight divided by unit molecular weight of the repeat unit. So, what it means is that you are effectively trying to find out how many times the repeat unit has been added, right. So, m bar n is the number average molecular weight, and this which is maximum of the two. So, weight average versus number average is relatively higher, and then m is the molecular weight of the repeat unit. So, you effectively are saying that the repeat unit has got repeated so many times. So, now if the degree of polymerization is more, the molecular weight is more, and therefore, the melting point is more, the strength is more. So, everything is correlated with the degree of polymerization. If it is just a monomer, very little strength, but if it has got polymerized over thousands of units, then the strength builds up, and particularly if it has got cross-linked, then it is even more. So, basically it is important that one investigates the properties from the structural point of view. So, this is the way we calculate the molecular weights and the degree of polymerization. So, this is the, I have described to you the concept, but then this is the way you actually calculate. Assume the molecular weight distribution shown in the figure for polyvinyl chloride. So, this is the distribution for polyvinyl chloride. For this material, compute the number average molecular weight and degree of polymerization, and see the weight average molecular weight. So, now you have different ranges of molecular weights, and molecular weight range in gram per mole, and mean is also given in gram per mole. So, mean molecular weight is given in gram per mole, and this is the numbers. So, if you were to get the number fraction, so that is given over here. So, this is a mean molecular weight in this range, and then so in every range you need mean molecular weight to characterize this range of molecular weights. So, while calculation you use this multiplied by this, and then divide by the total molecular weight, and that will give you 21.15. So, to determine the degree of polymerization, we first it is to compute the repeat unit molecular weight. So, for PVC it consists of 2 carbon atoms, 3 hydrogen atoms, and single chlorine atom, because we have seen that in polyvinyl chloride a monomer, you have C2H2. So, you have C and C with each carbon atom having 2 hydrogen atoms, and then the remaining 2 bonds being reserved for polymerization. So, the H, one of the hydrogen atoms, is substituted by a chlorine atom, and that is what we call as polyvinyl chloride. So, now you have 3 hydrogen atoms, 2 carbon atoms, and 1 single chlorine atom, right. So, the atomic weight of carbon is 12, hydrogen is 1, and chlorine is 35.45 gram per mole. And so, for PVC, m is given as, the small m is given as 62.5 gram per mole, and the degree of polymerization, which is average degree of polymerization 21,150 gram per mole, is therefore it gives you that 338 times is the number of repetitions the repeat unit has been added. So, basically one macromolecule therefore contains 338 repeat units of vinyl chloride, right. So, vinyl chloride is CH3Cl, right. C2H3Cl is the uh, formula for vinyl chloride, and when you polymerize this, you get when you polymerize it a number of times, let's say 338 units, you get the kind of average molecular weight that you have calculated. So on an average, the number of chains are chains contain 338 units of vinyl chloride. Now if you take the maximum range, you take the maximum range where 37,500 is the mean MI. So there the number of times this single monomer has been repeated will be much higher. So basically in each of, so here on an average it is 338, but here it is going to be much higher than the average, here it will be much lower than the average. So wherever it is lower than the average, you will have lower melting points, lower strength. Higher than the average, you will have greater melting point and greater strength, whereas wherever you have the average, you have an intermediate melting point and intermediate strength. So now when you mix these polymers or macromolecules of different molecular weights, it correlates with the kind of strength you are looking for in the final product you make. It has to do with the final amount of strength that you want to generate in the application, and therefore you would select the molecular weights depending on their mechanical properties as well as the melting points of each, and accordingly decide the processing conditions. Now because of the chemical nature of polymers, basically they are bound by covalent bonds. If you repeatably heat them, let's say you use the polymer, make some article out of it, and then later on you find that okay, this article has ended its life, or it's of no use anymore. You can recycle that polymer just as you can remelt the metals n number of times. Similarly, thermoplastic materials like what we are looking at now, polypropylene, polyethylene, poly-PVC, so these are all thermoplastic materials which, like metals, can be repeatedly molten and they can be reused. So you are tired of using one particular plastic article, you can melt that polymer and then cast it into something else which you are going to use. Now there is a catch over here. The catch is that because of the chemical nature, when you do repeated recycling, that is repeated heating and processing of the material, the amount of time the material stays at a particular temperature decides the rate of degradation of that particular polymer. What it means is that if you have a macromolecule which has got, let's say, 338 times repetition of the monomer, and then you have repeatedly heated it and reused the same polymer several times, it is not going to have a macromolecule with the same 338 repetitions. The number of repetitions will be less. So the macromolecule will become smaller and smaller, its melting point will become lower and lower. So if you want to adjust the melting point of a given material, of a given polymer, then it is important to have a balanced mix between relatively high weight molecules and relatively low weight molecules. So it is of engineering use or engineering application to have a different distribution of weights of different sizes of polymer molecules. So to different extent of polymerization and a mix of different extent of polymerization in a given sample of raw material is very useful from a practical point of view. So it's not really a drawback, provided you are able to design your component and you are able to design the material which is consistent with the strength that you want at the end of the day. Now, so this is another problem. Here we were talking about number fraction. Now we have average molecular weight. So what changes here is the weight fraction of each of these molecular weight range. So it is just 2% of the macromolecules lies within this polymer range weight. So here the number of times the chain would be repeated, the monomer would be repeated is the smallest, and the percentage is just 2%, and so you have the W weightage into the mean gram per mole is therefore is giving you 150. So this way you have this product, the weighted product of the mean mass or mean mass of the for every range of macromolecules, and then you get the mean average molecular weight as 23,200 gram per mole. So that is the macro. So for macromolecule, so this is the kind of weight that you get. So now what kind of macromolecules can you have? So we have seen that we have by virtue of chemistry you have a repeat unit of a specific composition. Then you have repeat units of different sizes. For example, we have seen that PMMA type of repeat unit is much larger than even PVC or polyethylene or polypropylene. There are other types of molecular characteristics, like you have different chain twisting, entanglement type of things. So you have multiple chains in the macromolecule, and then they get entangled with respect to each other. And so arrangement of these chains, whether they are branch chain or single long chain, whether it's a branch chain or they are entangled chain. So when these chains entangle, again it generates a different set of properties, a different kind of mechanical behavior, different melting points. So one can tailor these the polymer behavior to your needs by using an appropriate composition of molecular weight. So you can have any property that you want by combining appropriately the different sets of molecular weight. Of course, supposing I want a certain melting point, I cook up a composition of a different combination of molecular weights, I cannot guarantee that I will get a particular value of strength. So what I can guarantee is I can get a specific melting point for which I have designed that particular molecular weight distribution. But then there is no guarantee that the strength which I desire might be obtained. So that has to be understood. So it's not that everything can be. So if you derive a molecular weight composition or constitution for a given polymer, then the objective is important. So if you have done it for strength, then you would have introduced certain macromolecules to increase the strength and so on. But then the melting point will be decided by the corresponding number of molecular sizes present in the entire mix. So the processing conditions will have to be set depending on whatever the material demands. Then you have structure, which is linear, branch, cross-linked or network structure. As I have already told you that you have a cross-linked structure means that there are linkages which are formed in various directions, due to which the links are unable to move with respect to each other. I told you that deformation takes place when the polymeric chains are able to move very easily with respect to each other. But then if they get cross-linked, then the degree of freedom of every polymeric chain gets curtailed, and as a result the freedom of movement being restricted, the polymer behaves very hard or behaves very rigid. So these cross-linked polymers therefore would behave much stronger as compared to the ones which are not cross-linked. So the material is the same, but then because of the arrangement of chains, you have a different set of strengths and different sets of mechanical behavior. Now compare this with metals. Now just as we have face centered cubic, body centered cubic, HCP and these types of different arrangements, due to which again we have seen that the crystal structure itself affects the strength of the material or orientation of the planes, certain planes with respect to the direction of applied stress affects the structure. Now here the structure means the arrangement of polymeric chains, how the polymeric chains are arranged, whether they are branched or not branched, whether they curl over each other and then they form a regular array of atoms or not. So these are different arrangement of these polymeric chains, whether cross-linking is present or not. So depending on the configuration of the polymeric chains, you will get different properties, different melting points. And like unlike metals where there are a certain number of atomic arrangements which remain fixed, here there is no such thing. So the atomic arrangements can be you can have regular and irregular atomic arrangements, because the methodology of forming a regular arrangement of atoms is completely different as compared to metals. So that is the reason why there are the behavior of polymers is so vastly different from that of metals. So you have these isomeric states, and so you have stereoisomers and geometric isomers. So you have isotactic isomers, which means that the so-called functional groups or so they will be on one side of the carbon atom. Atactic would mean that they can be on both sides of the carbon atom. So we will see a few examples as we go along. So let us have a look at the examples for a good understanding. Okay. So you have the shape of the molecules. So you have if you look at the shape of this molecule over here, so this is just a small chain. This is got polymerized into 3, and now you have got a slightly different configuration of the chain. So this shows how the configuration of the chain affects the properties, and so it has got different degrees of coiling, bending, and so on. So you have you see that for the rightmost atom may lie anywhere on the dashed circle and still subtend a 109 degrees angle with the bond between the two atoms. So the path of movement of this atom can be 109, can be a full circle, and still it will subtend 109 degrees with respect to this bond. So so degree of freedom is much more. On the other hand, you have straight and twisted chain segments are generated when the backbone atoms are situated as in B and C respectively. So these are the this is a straight chain and these are twisted chain, because now the chain has got twisted out of its plane. So what it means is, so this is a straight chain but with several bends, but then the bends are not in the same plane over here. So that's what generates a twist in the chain, and you see that the paths of these atoms are interfering with respect to each other, and that is where the hindrance to movement comes into play. So basically how each one of these polymeric chains is going to behave depends upon the degree of freedom which is enjoyed by this atom, which is enjoyed by that atom. So this atom would move in this direction, along this dashed circle, and if it has the freedom to do so, then yes, it will be easy for the deformation, for anything that causes polymer chain movement. Whereas if there is an interference between this and that, interference between that and here, then you are going to have this movement a little difficult. So this twisted chain type of arrangement therefore would have a greater resistance to movement of chains, and therefore greater resistance to deformation when it comes to trying to either process the material by extrusion or deformation processes. Similarly, when it comes to melting also, the response to heat of these polymers. So these will not soften as quickly as this will. This will soften the quickest maybe, and this will soften less quickly, and this will soften even less quickly, right. So the single polymer chain molecule, so this is single polymer chain molecule that has numerous random kinks and coils produced by chain bond rotations is shown over here. So this is the macromolecule, which is a long molecule which has got so which is composed of three. So partly it is a straight chain, and partly it is a twisted chain. So it is a lengthy, highly lengthy macromolecule having all these three features built into it. So such macromolecules therefore are bound to have very high molecular weight, and they will also have much greater strength as well as melting point. So each polymeric chain can therefore be seen as a spring. Okay, now let us say that you have just one spring, you can pull it and then release it, it comes back to its original position. So similarly, every chain is every polymeric chain is like a spring, and then when you have branch polymeric chains, something like this, you have springs branching off from the central one. And now if you say that the springs are interlocked with respect to each other, then you will realize that the degree of freedom that each spring enjoys to extend and come back becomes more restricted. So you have greater and greater strengths as cross-linking takes place, as you see over here. So if you have just a single chain polymer, then you have van der Waals and forces and hydrogen bonding between the chains. So this hydrogen bonding and van der Waals forces are the ones which dominate in polymers. That is because you have polymer chains, sections of polymer chains interacting with one section interacting with the other section of the polymer chain, or two neighboring chains interacting with each other. So you have what is called a steric hindrance between two hydrogen atoms interacting with each other. See, a steric hindrance is the result of two atoms. Let us say you have two polymer chains. You have two polymer chains, and I have one hydrogen atom here, another hydrogen atom there, and then the electrons of these two hydrogen atoms. So there is one electron per hydrogen atom, and then as the two hydrogen atoms comes together, there is kind of repulsion that takes place between the two. So this prevents two polymeric chains from coming together, because the hydrogen of the atom in this polymeric chain and hydrogen atom of this polymeric chain, if they come very close together, they cause repulsion due to what is called a steric hindrance. So that also gives the strength to the material, because now if you are trying to compress the material, then beyond a limit it will have very high strength, because you cannot overcome the repulsion. So the strength would increase depending on the extent of compression you apply, and then when you remove the load, there will be a significant release in the strain, because you are compressing it against the forces of repulsion. When you have released the load, once the force that was forcing two chains together is gone, the chains immediately come apart, just as a spring would get released, right. So that is why I compared these chains with springs, because as long as the load is present, the springs would remain compressed, but once the load is removed, the springs will come back to their original state. And that is the reason why these polymer chains behave the way they do. So you have a rubber band, you have many such things. So when you stretch it, the polymer chain is getting stretched. When you release it, the polymeric chain gets, when the load is gone, it comes back to its original shape. So that is why each polymeric chain resembles a spring. And then if you don't want this polymer to behave soft, you want to add strength to it, then you do the cross-linking, and then you get vulcanized rubber. So our tire tubes are made from vulcanized rubber, for example. So you add sulfur to it, which promotes cross-linking, and this sulfur results in cross linking of rubber, which enhances the properties of rubber. So basically what we have seen is that if you have a 3D network of molecular structures like polyurethanes, epoxies, phenol formaldehyde, etc., then you have macromolecules which themselves are relatively strong, which melt at much higher melting points, and then when they are cross linked, they become further stronger, and therefore many structures like tools, for example, would be made from polyurethane, epoxies, and phenol formaldehyde type of materials. So typically polyurethanes are used for tool materials with relatively low life, but then these are modern tool materials which are relatively light. So if you want a lightweight tool, then you can make it from this particular material. So it will so the strength is derived from cross linking, extensive cross linking. So I think I have given you a fair idea about how the polymers derive their strength. They derive them from a chain like arrangement, and the disposition of these chains relative to each other, and the configuration of a single chain, whether it is branched or whether it is curled over each other, whether it is cross linked. So it all depends upon how the polymer chains are configured, and the strength comes from there. So we will continue this topic in the next class. Thank you.